So let's get started. So welcome back, everyone. So it's that point in the middle of the semester where I think there's a lot going on. So we're about 2/3 of the way through the semester, and so we're talking about dimensionality reduction. Yeah, so I just want to briefly cover kind of review what's going on in the schedule. So we had the first lecture on dimensionality reduction, kind of introduced the idea, started talking about the SVD. We didn't quite get as far as I had hoped in the lecture, so I'm going to try and keep this sort of brief. And then at the very end of the lecture, I want to save 2 minutes and kind of discuss kind of homework 3, which was due today. I realized quiz 4 was last week on Monday. The initial spot check I looked at that, I think most people did pretty well. I haven't gone through the last question yet. I know some of you had some kind of challenges on this question. I asked you to write stuff in LaTeX. Hopefully you're, or at least in the essay part, you're a bit more comfortable with that, but we'll try and be generous in grading that, whether you got the main idea or not, whether everything was perfect or, yeah, we definitely won't worry about simple notational issues, but we'll try and be flexible. And I know that's a little more challenging to write in Canvas than on a piece of paper. So we'll have this lecture, then the next one, which will talk about some algorithms, and then there'll be a break in the schedule, and I'll hopefully give you a little bit of chance to recover during the middle of this challenging semester. Sure. So let's get back into the lecture, because there's a kind of a lot of stuff I'm hoping to cover today. I'd rather go at a more gradual pace and make sure people are understanding and really getting it than cover all the material. I think I've structured it from the most important stuff towards the kind of first. So what we cover will be great. So we had started to talk about the SVD, which is the singular value decomposition. And the input to this is going to be a matrix A, right? So A, and this is going to be a matrix in Rn by D. Just remember, this means that we have n of these rows and d of these columns, and we'll be particularly interested in these objects like AI and AJ, and we'll think of these as, and these are kind of the rows in this matrix. Think of these as data points. And the right way to think about this, at least in the context, SVD has lots of applications in lots of places, but within data analysis, the main application is when you think of AI and AJ, as these points in RD, these d-dimensional data points, and you assume, very important, that if I can look at this distance between them, think of this as a distance, as some sort of distance between AI and AJ, as like a distance between them, and this makes sense. Okay, by that, one way of thinking about this is that they have the same units in all of their coordinates. I'm not having height and weight in here because this norm is adding these components up. And if I change the unit in height from centimeters to meters, completely change the relative ratio of those two components without changing the information content about it at all. So all this will be predicated on this. There's other work and how you can move beyond this in the later chapters, sections of this chapter in the book that we won't cover in this class, but there are a lot of uses even with this case. And I went through some example data matrices that where this data like this arises, and having a distance between these two data points makes sense. So okay, so this was, and our goal is going to be kind of a low dimensional then representation of these points. And I briefly talked about this singular value decomposition. And so let's see. So this kind of decomposes A into the product of these three matrices, U, which is going to be in Rn times n, and this is going to be is going to be an orthogonal matrix. Okay, there's S. Okay, S is going to be an Rn cross D, so it's the same dimensions as A, except all the information is going to be on the diagonal. Right, so I'm going to have elements on here. We're going to call these sigma 1, sigma 2, right, up to sigma D. Okay, and everything else is going to be zeros, right? So all of this is all going to be zeros, and also the off diagonal stuff is going to be zeros. So there's really only D values that are captured in here. Okay, and then finally there's another matrix, V, or actually V transpose. So V transpose is going to be over here, and this is going to be in our D cross D. So it's a D by D matrix, right? So all the multiplication works out. I have D by D times an N by D. That gives me an N by D matrix again. Multiply that by N by N. That's still N by D matrix, right? So I get back the right dimensions of A. Okay, good. This decomposition, which will be built into all sorts of things, and we'll talk about algorithms in the next lecture for how to create it, is going to output these three matrices. And if I multiply them back together, in every language uses the same backend, multiply them back together, except in Python where they compress stuff and you have to open it up a bit, but I'll show an example of that. Multiply back together, I'm going to recover A, but these matrices capture a lot of really special structure. So matrix multiplication, the order of matrix multiplication does not matter. I can multiply U times S and then S times V transpose, or S times V transpose and then left multiply it by U. The ordering, the left to right order matters, but not the order of operations. And actually there's an algorithms problem is the runtime of multiplying together a bunch of matrices actually depends on the order of operations. I can compress really big matrices to small ones first, and then that saves on the runtime. Okay, but in this case, there are only three matrices here. Okay, so the kind of the left to right order of them is important, but not the order you multiply them in to get the same answer. Yes. Okay. So I want to start by talking a little bit about the structure of the SVD, and then I mentioned very quickly at the end of the last lecture how you get this low rank or this low dimensional subspace approximation. We'll see more gradually where that arises and how you can do that. So okay. So I want to. Yeah, so first I want to label these things a bit more. The columns of U, call this UI. These UI are called the left singular, left singular vectors. These are going to have the property that the norm of each UI is equal to 1, and UI dot UI dot UJ is going to be equal to 0. So these are going to be orthogonal with each other. Okay, so the orthogonal matrices, and similarly, these are going to be Vi is going to be the right singular, so vectors, and I'm also going to have the norm of each Vi is 1, and the dot product of Vi and Vj is going to be equal to 0. Okay, so these are the right singular vectors. This is V, that's a V, so a V transpose, that's going to look like a row here. That's one of the rows of V transpose. Okay, and so these rows are going to be orthogonal to each other. Okay, and so these matrices, basically, so in general, these are orthogonal, so matrices. They have no scale information. Okay, so if I take the norm of V, say V transpose X, that's going to be equal to the norm of X, or multiplied by V. So if I multiply a vector by right multiplied by V transpose or left multiplied by U, I'm not changing the scale of anything here. If you remember about the linear algebra lecture discussion, this is basically changing the basis of this. I'm just kind of rotating the basis. I'm saying instead of having the original X and Y axes, I'm rotating these to have new axes here. Okay, and we'll see a little bit of a demonstration of a picture of this, but it's not doing the scale, it's just kind of changing the basis. And then this S matrix in the middle is controlling all of the scale information about A. So I've kind of decomposed A into a basis along for the n dimensions representing kind of the rows, and a basis on the d dimensions representing the columns. And then along that, I've got scale in the middle. The S matrix is determining the scale, how much, if I multiply by the matrix, does it get bigger or smaller? That's determined by S. Okay. The other thing about these orthogonal matrices is that U times U transpose is going to be equal to the identity matrix. We mentioned this before. This is also going to be true of V times V transpose is also the identity matrix. If you remember, each row dot product with itself is 1. Its norm is 1, but with anything else is 0. And if I multiply all these out, and so that means that U transpose is equal to U inverse, and V transpose is equal to V inverse. Okay, so I get the inverse for free with these, and this will come and be useful a bit later. Okay, now with these, the scale matrix, so this controls all scale information about A. Okay, and I'm going to have the property that these singular, so values are going to be ordered sigma 1, right? This is equal to S11, the first entry in the first row, and similar on the diagonal. It's going to be greater or equal than sigma 2, greater or equal to sigma 3, and this is up to sigma R, and then these are all, let's see, greater or equal to 0. The rest of them are going to be 0. Okay, where R is equal to the rank of A. Okay, so we'll talk about, again, more about how to think about the rank, but remember, the rank of A is the number of the linearly dependent rows or columns, the maximum number I can find in A, and this determines how many singular values I have. So one way to determine the rank of a matrix is to compute the SVD and count the non-zero singular values. Okay, and I get up to the rth singular value, and then everything after that is 0. Now, numerically, sometimes these things look like they're almost 0, but not quite. And there might be some small numerical precision here. But generally, these algorithms do a pretty good job of getting that to be exactly 0 in a lot of cases. But sometimes you need to watch out for that. Okay, and so they're in decreasing order. So that means in particular that this guy, the top singular vector, which corresponds, this is what's multiplied by the top right singular value and the top left singular value. This is the most kind of important. So the one highlighted here. Okay, so this is kind of the most important element. And how much more important it is based on its value. Okay, now in particular, it's capturing something like the variance. It's saying this direction has so much variance, and after I factor that out, then I look at all possible orthogonal directions, and the second one captures the one with the second most variance. Okay, it's not quite variance yet. When we talk about PCA, it'll be a lot closer to variance. It's kind of the average squared error. In this case, from the origin, when we do PCA, it'll be the average squared error from the mean, which is basically the variance again. But okay, so think of it as how much variation in the data is being captured along kind of this subspace spanned, kind of described by the first singular vector, the first singular value, and both the right and the left singular vector. Okay, so this is kind of some information, but there's a lot going on. So let me try and provide a different way of thinking about this. Okay, I'm going to provide a couple different ways to try and conceptualize what's going on, probably a few. Okay, and the first one, I think geometrically, so I'm going to give you a geometric picture. So I like to think of something like an aggregate shape of the matrix. So let's think of an example where A is kind of a subset of R2. Okay, so that means, think of it as a bunch of these data points, A1, A2, up to AN. Okay, and we're going to have this, so this coordinate space, and let's assume that they're kind of centered around the origin, and that'll make more sense for now. And each of this might be A1. This is an R2. Remember, this is R2 in this picture, although it works with higher dimensions, but I can't draw that. There's A2, A3, A4, A5, A6, maybe A7. Okay, and so there's data that kind of looks like this. Each one is we can also think of this as a matrix, but now it only has 2 columns here. Okay, just so I can draw a picture. And now I can realize I can find the top right singular vector, V1, this will look kind of like in this direction. Okay, so remember V1, the norm of it is going to equal to 1. Means there's basically a circle around here, a unit circle, and it touches this unit circle. This is V1. And it's somehow capturing this subspace, which is kind of has the most variance along it, right? So there's a one-dimensional subspace. And the idea is if I projected all the data onto this blue line, that is the line that has the most variation on it. If I'd done the orthogonal direction, they're more scrunched up. And I'll draw that direction in a second here. Okay, so that means V2 has to be orthogonal. So let's say V2 is here. Okay, and that there's this other subspace. Let's already, right, that's going to go through here. This is the V2 subspace. And if I were to project, let's see what happens if I project all these onto V1. There's going to be onto this subspace, I kind of want to measure kind of looking at these, how spread out are these points. They're fairly spread out. They're still pretty far away from the origin, where if I did this in a similar way with, say, this V2 direction, they're going to be more scrunched up. Scrunched up is a technical term here, right? not actually a technical term, but okay, but they're kind of more compressed here, right? They're more compressed along this kind of space, okay? So the V1 direction, the one I'm finding, is the one that keeps them as stretched out as possible. Okay, so now when I talk about aggregate shape, there's kind of implicitly this sort of ellipse structure that's kind of going on here. I'm trying to draw this ellipse, okay? And an ellipse is kind of like a, it's an oval or whatever. It's a circle that's been stretched out, but it's still like parabolic, right? So it's the sublevel. So if I drew a parabola and I picked a centrally symmetric parabola, and I drew an iso level where all the function values the same, that's what an ellipse is. And this corresponds with actually having two axes. V1 and V2 are going to be those axes, and a scale. And that scale is going to be exactly basically times sigma 1, and this is V2 times sigma 2, tells me how much to scale this out to get this shape. And so there's this elliptical structure, and that kind of goes along with the variation of the shape, right? And so this has the property that if I pick any unit vector x, right, this is x some point in RD, okay? And now I'm going to look at the norm of AX, right? So A might scale it. Well, how much is it going to scale it? How much it scales it is going to be determined by this ellipse. That tells me basically this length of that pink curve here is going to correspond with the norm of AX. And so this is going to have this, this is a parabolic structure. Once you remove the square root, it's kind of a sum of squared effects from all the data points. I'm taking x, I'm dotting it with basically this norm is going to be equal to I equals 1 to n of the dot of x of AI squared square root. Okay, so I'm dotting with all the points, and it tells me how much variation, and this is kind of one of these quadratic forms, and that gives rise to this ellipse, this sort of shape that pertains to the data. This definition down in the bottom I've written has basically nothing to do with, it doesn't directly show you these right singular vectors, but it gives rise to this sort of elliptical structure here. It gives rise to this structure, and then the axes of this ellipse are exactly the right singular vectors. And this is true in higher dimensions as well, but I'll just drew it in 2 dimensions here. Okay, so that's one way of thinking about this. Okay, well, let's see another way. Okay, so let's look at this. I'll start with an actual example. I'm going to kind of draw some pictures, and then we'll go through and see this in Python as well. And Python, the main thing I don't like about Python is how it deals with the SVD. But it's a little finicky in how it represents things. That's within NumPy and SciPy. But we'll see that. So okay, so I'm going to have an input here A, and right. So these, let's see, what do I want to do? These rows of A. This is going to be this is A1. This corresponds with 4, 3, which is a point right here. This is A1. A2 is right here. A3 is A3 and A4, right? So I've drawn a picture of these data points. You can kind of think in your head where this elliptical structure is that surrounds it. With 4 points, it's not kind of saying much, but it's there. And it outputs these 4 matrices, right? U, S, and V. In this case, V and V transpose are the same. With 2 by 2 matrices, that's often going to be the case. Okay, but if I multiply back together U, S, and V transpose, I should recover A, and we'll see this in Python in a few minutes. So okay, what I would like to think about here instead, though, is we're going to go and do this experiment a bit more here. This is R2. So this is N by D, which is 4 by 2. So I have a 2-dimensional space. And I'm going to start with so I'm going to have a unit circle. And I could try and draw these on top of the points, but it'll get cluttered. And I'm going to start with a single point, which I'm going to call X. And in the example we're going to go through that I've worked out, 0.243 and 0.97. This is approximately a unit vector. I trimmed off the decimals so we can write down something concrete, but this is approximately a unit vector. And what we're going to do is we're going to multiply. I'm going to see what happens with AX and also with, I said that A was equal to USV transpose. So I'm going to see what also happens to this by looking at this into 3 steps, into V transpose times X. Then I'm going to take the result. The result here will be P. Do S times the result of P. That's going to give me Q. And then I'm going to recover this back. And we're going to get some vector Y. And we're going to see is the same. OK, but I wanted to see what each of these steps are doing with this vector X. OK, so the first step what we're going to do is we're going to multiply. I'd like to figure out what happens when I do V transpose times X. What's a picture that we can see what's kind of going on here. Okay, and the first step towards doing that is drawing the right singular vectors. Okay, so this guy is V1. Where is V1? Okay, V1 is negative 8.1, which is about here, and negative 5.8, which is about here. So that means that V1 is a vector that looks like this. Okay, this is the vector V1. V2 going to be similar. It's going to be the x-axis is V2 now is going to be, this is V2. It's going to be negative 5.6 about here, or negative 5.8 and about 8.1. It's going to be about up here. So this is going to be V2. It's going to be a vector here. And indeed, these should be basically orthogonal to each other. Okay. If I wrote out all the decimals, they'd eventually be perfectly orthogonal. The dot product would be 0. Okay. Good. Okay. So what happens when I multiply x by this? Well, so the output, it turns out, is going to be, well, it's going to be another point P, right? So I'm going to say that this is going to be a point. Let me write this in red. This is going to be a point P. It's going to be Vx. P is also going to be in RD, right? And in fact, P is going to be equal to V1 dot x, comma, V2 dot x. These are going to be the 2 coordinates. That's what matrix multiplication is doing. The columns of V, the right singular vectors, are going to be, so I circled the columns. Let me erase this. It's the columns of V transpose, but it actually should be the columns of V and the rows of V transpose. they're the same in this case, so we're wound up okay, but they're so V transpose is gonna, is gonna be the same thing, but I'm dotting X with V transpose. So the first coordinate of P is going to be V1 dot X, second coordinate is V2 dot X. Okay, and I can write down what the answer is. It's actually not so important here. What's more important is actually to think about this, what this looks like. And I'm basically getting this new basis with V1 and V2. Okay, and there's still going to be a unit circle that's happening here. V1 and V2 are both these unit vectors, but now they're representing my coordinate axes, and I need to write this point X in the coordinate axes, right? So along V1, I'm going to get a value about here. So the V1 is about negative 0.8, right? So the V1 coordinate is going to be about here, and the V2 coordinate is going to be about 0.6, right? So it's still going to be a point here. This is going to be P. This is the point P here, right? Again, this is V1 dot X. That's the first coordinate, and V2 dot X is the second coordinate here. Right, so it's still a unit vector. Remember, the orthogonal matrices do not change the scale, so that if it started a unit vector, it's going to stay a unit vector. If it started a length 2 vector, it's staying a length 2 vector here. Okay, so it's not changing the scale, but it's changing the basis, right? I've changed the basis into this V1 and V2 basis here. Okay, okay, good. So this is kind of cool. So now what happens if I'm going to, now we're going to see what happens if I say Q is going to be S times V transpose times X, which is going to be S times Q. Okay, it's easier to think of S times P, S times P, the output where V transpose X was P. So now I do S times P. Well, this is going to be pretty kind of simpler to do now. This is a kind of like an identity matrix. It's a diagonal matrix, but I'm scaling. I've scale along these diagonal elements, and they tell me specifically now how the coordinates are scaled. Right. So 8.16 is telling me how the V1 coordinate is scaled. Okay, and 2.3 is telling me how the V2 coordinate is scaled. Okay, so let me try and draw this now with more space. Now let's say this is V2, this is V1. Remember, and I ended up with my point P about here. Okay, and now I'm going to do P times S, and S is equal to 8.1, and what is this? 8.1 and 2.3, 0, 0, 0, 0, 0, 0. Okay, and so what's happening is I'm going to take the X coordinate, and if I think of this kind of this unit circle, the unit circle is being inflated into an ellipse here. Okay, so this goes up to about, this is now a distance 2.3, and if I extend it out here, this would be a distance about 8.1. Okay, but what I'm interested to is to scale P, and P gets scaled out to here, out to Q. Okay, so Q has now been scaled out in this way. I've scaled the V coordinate by 8.1 and the V1 coordinate by 8.1 and the V2 coordinate by 2.3, and I'm going to get this value Q. This is 8.1 times P1, 2.3 times P2. right? So that's how I'm going to get it out there. Okay, except this was actually a little bit of a lie. I'm actually going to get 2 more coordinates, but they're going to be zeros, right? So this ellipse is actually a super flat ellipse, right? It's got the long direction and the skinny direction, and then there are 2 more directions that you can't see, which are coming out of, out of this plane here, but I've scaled them by 0, so it's fine. And then the U matrix, which I won't draw, we're in 4 dimensions now. It's going to do a rotation of this basis, right? So it's now in 4 dimensions, and it's doing a rotation in this 4-dimensional space. Okay. Okay, so let's quickly go and see this so inside Python. Okay. All right, we're back looking here. So we're going to now use NumPy to represent stuff, but this linear algebra operation is in a library called SciPy. Okay, and there's a linear algebra package that we're going to call LA. We're renaming that. And then, so we're going to set up this as our same matrix A as before, and we're right, and I'm going to call this built-in thing called SVD from the linear algebra package. On A, I'm going to get out 3 things: U, S, and V transpose. In Python, it gives you V transpose directly, so you don't have to you're not getting V, you're getting V transpose. And S is only going to give me the stuff on the diagonal. It's not going to give me the full matrix here. Okay, there are ways you can have it output other stuff, but let's just see the standard output here. So I'm going to get, this is going to be U. This is the U matrix here. This is the 4x4 matrix, the same one I had on the slide before. This is S 8.1 and 2.3, and this is V transpose, which we had looked at. Right, here's S and V transpose again. Okay, and here is now my vector X. And I did a thing to force it to actually be normalized so we can check that the norm stays 1, right? So here I printed out, this is, I can also do, say, print norm of X. Yeah, so, well, okay, so it's not exactly 1, but yeah, that's 1 pretty much, and it stays 1 after this transformation. And here's the value P. It's negative 0.76, negative 0.64. My estimation of those values was pretty close. Okay, now S I can reconstruct. I can reconstruct a matrix uppercase S from here. This gives me back a D by D matrix, which is the diagonal square matrix. And I can multiply that by P, and I can get Q. And I basically just scaled, right? This is now 8.1 times negative 7.6, and that gives me 6.4 here. And now the norm has increased. The norm has increased from 1 to 6.3 at this point of Q. Okay, I didn't get back this N by D matrix, which is standard in other kind of, in MATLAB, that the default is that what it gives you. So if I want to multiply by U, I need to kind of expand Q into a 4-dimension. So I'm going to create a 2-dimensional 0 matrix and then concatenate it on here. And so then if I see Q4 I've printed down here, now it has 2 more zeros on it. Now I multiply that by U, and I'm going to get back this vector Y. Okay, and this should be the end result of A times X. And let's check that. I take X again, and I multiply it directly by A, and I get back the same vector. So that's great. Okay, and I can also see that I can recover A from U times S times V transpose. Again, because it gave me this kind of this trim version of S, I had to concatenate a zeros matrix on the bottom here. But if I do that, I'm going to get back A. Okay, so again, there's some like, to get this working, there's a little bit of linear algebra you need to do in Python, but it's this built-in SVD call. Again, this is the same, calls the same library that is used in MATLAB, or if you use, directly the Fortran code. So LAPACK, anything uses the same LAPACK library underneath. So, and next lecture, we'll see one way how to actually compute these things. Okay, any quick, I can't see the chat. Let me reopen the chat here. Okay, that S isn't what's in the slides, I think. Let's print. S is, yeah, I think that's the same. So the S is only different in that it doesn't have all the zeros in it, but otherwise those are the same numbers. Maybe there's a small rounding error or something, but those should be the same numbers in S. At least I'm seeing the same numbers in my book that I copied from and pasted into the slides. But if not, try yourself. If the slides had a typo in them, then that's probably the slides' fault, not actually the fault of LAPACK or NumPy. Okay, let's jump back to our lecture. Okay, great. We're back here. Let me get my other windows back up again. Okay. Okay, great. Okay, so next want to talk about, there are kind of two more interpretations of what's going on here. I'm going to talk about, let's see, so the best rank K approximation of a matrix here. So we're going to get to this idea of a best rank K approximation of A. Okay, and so we're going to get another matrix, and what this is going to be a B matrix in R n times D. So rank of B is equal to K, and typically K is going to be less than D less than N. Okay, we can switch N and D, so N is less than D, and everything is a transpose of what's going on here, but K will be less than the original rank. So we want a lower rank. This could be 2 dimensions, right? So we can visualize it. But so to minimize either, so if they're the same dimensions now, so I can subtract them, either the spectral norm or it's actually both of these are going to be true at the same time, minus B the Frobenius norm. Okay, and I'll review what these are. The spectral norm is kind of this maximum one direction, and the Frobenius norm is the sum squared of all the directions here. We'll kind of recover those definitions as we go through the kind of the derivation of how SVD gives us this answer. So, okay, so let's start by remembering what is sigma 1. Sigma 1 is equal to, this is the top singular value, singular value is going to be the sum over I equals 1 to n of the dot product between AI and V1 squared. Okay, so this is one way of recovering what this is. This tells us how much squared variation is along this V1. And in fact, it's equal to the max over all V in RD such that V equals 1 of this sum. So if I look over all choices of V that have a length of 1, then this is the top singular value. Okay. Okay, and similarly, V2 is going to be I equals 1 to n, or in general, Vj is AI dot Vj squared. But I can find V2 by saying, okay, it's all of, in general, sigma 2 is going to be max of all V in RD such that V equals 1 and V and dot V1 is equal to 0. So it's orthogonal to this and then this sum. Okay, squared. Sorry, let's. Okay, so these are what the singular values are going to recover. They're recovering how much variation is along the subspace, and these are orthogonal components. Okay, and so that means that because they're orthogonal components and squared norm by the Pythagorean theorem, so I'm able to say the following. Yeah, so pi of b of a, now if I just look at a single value a, pi of the projection of a onto the subspace by b, which is going to be represented, remember that I'm going to have defined by these vectors v1, v2 up to vk, right? This is going to be defined as kind of the sum of j equals 1 up to k of vj dot a vj, right? So it's giving me that norm, the length based on the a dot vj times this direction vj, and they're orthogonal. So I'm getting kind of I'm filling out this k-dimensional subspace in a d-dimensional domain by these vectors. I'm adding one component at a time to these. Okay, and so that allows me to think about this, the air, right? The leftover air is going to be a minus vb. This is the distance to this projection, right? So if I have this, let's see, so I've got this original space. I'm going to have this v1 and v2, this new space, and now I'm going to have and let's say I'm going to, right, there's a two-dimensional subspace here. Let's say original, we're in v3. Now I'm going to have, let's say this is, okay, so now I have a point A, and I'm going to project down onto here, right? I'm projecting down onto the space. This is going to be pi of b of a. And then the distance, I want to measure this distance, the distance from A to the projection down to that subspace, that's going to be this distance right here. Okay? So I want to measure what this distance is, and I'm recovering the parts along coordinates v1 and v2, but not, and up to vk, but not the ones all the way up to d. There are these other components I'm missing, right? So I can write down that the distance, which is what is left, is going to be the sum over j equals 1 to d. So I can, remember, I can recover a exactly from a basis, a vj. This gives me, this term here is a, okay, minus sum just up to k of Vj a Vj. This here gives me projection onto B of A. Okay, so yeah, let's do the squared norm. Okay, and this is going to be, so that's, and then I can just write this then as J equals K plus 1 up to D of A Vj squared. Okay, so I'm going now, the part that's left, the squared norm, which is remaining, the distance, is the components of A in the other directions, the other Vj vectors, which I didn't have in my subspace. Right, so every Aj can be made up of two components, the part. So I can think of this as having two components here. This is the part along the subspace, and this is the part that's left over, right? And it's the sum of those two parts. And by the Pythagorean theorem, these are orthogonal. The total distance, the total squared distance is the sum of the squared components, right? And I can write that this way. I can decompose it here. Okay. So this allows me to write the cost of a point that's left, and now my goal is to find the subspace B, which is minimizing the this cost, summed the squared cost, this squared cost over all the points, right? So now my goal is to find B. So in Rn by D, rank B equals K to minimize either the sum of I equals 1 to n of AI minus projection of B of AI onto B squared. This is exactly equal to the Frobenius norm of A minus B. That's the Frobenius norm. I'm just summing up the squared of all the components here. I can write, remember the Frobenius norm, I can write as I can take the squared norm of each row and just add those up. That's going to be the Frobenius norm. Or to minimize, instead of just the sum of those components, the sum along any one direction, right? So I can write the sum over all of I up to n. Actually, so I won't want to write this as the max of V in RD such that V is equal to is going to be equal to a unit vector. The sum equals I1 n of of just the dot product of V with AI minus just this dot product squared. Okay, so what this is saying is if I pick any direction in the space and I say, is there a direction that has a lot of variation left in it? I want that to be as small as possible. This is equivalent to A minus B squared, the spectral norm. Okay? Okay, and so it turns out if you set B equals to be defined, set B to be defined by this basis VB, which is V1 up to VK, where these are the top K right singular vectors. Okay, so if these are defined by the top K right singular vectors, then if if this is true, then I'm going to get that this is going to be equal to exactly equals 1 times v k plus 1 ai minus, yeah, so it just times ai squared. Okay, so which is exactly going to be equal to sigma k plus 1. Okay, so this last component, what is the most variation left after I factored out the first k singular, right singular vectors? Well, that's going to be the k plus 1 singular vector by definition. You kind of define these recursively by the most variation left after I factored out the k before it. And so that's what this spectral norm is capturing here. And I could have followed through and subtracted out. I could have put inside of here where I subtracted out the components projected onto B. But those components are going to be orthogonal anyways. If I dot product with those components, they're going to be 0. So I can actually ignore those there. And so I just need to multiply by AI. Because I already have, by definition, VK is going to be orthogonal to all of those components. And then that means that this term up here, this is going to be equal to the sum over j equals 1, k plus 1 up to d of the sum I up equals n times ai dot vj squared. Okay, so instead of just the vk term, the Frobenius norm is doing the vk term plus the v k plus 1 term. Here, actually, let me write this more clearly. This is going to be equal to j equals k plus 1 up to d, the sum of I equals 1 to n of all these data points of vj up to ai squared. And so I know each of these terms is going to be sigma j. So that means this is going to be equal to j equals 1 up to d of sigma j. Right, so it's not 1 to d, k plus 1 up to d. So the remaining singular values is going to be what's left over in this Frobenius norm. Okay, okay, so how do I get this best rank k approximation? I need to use one more property here. One more thing that I can see that's going on is going to be that that I can I want to think about kind of taking the say v1, sigma 1, and u1. So the top right singular vector, the top singular value, and the top left singular vector. And I can do sigma 1 times u1 times v1 transpose, right? So this is kind of taking the top one thing that's going on here, and this is going to be a matrix in n cross d, because I'm taking this is not an inner product, this is an outer product between the u and the v, and sigma is a scalar. So this gives me a n by d matrix. It's an outer product, but this is going to be rank 1. When I multiply by matrices, I get the rank of the product of them is no more than the smallest rank of any of the components. So this is a rank 1 matrix. And in fact, this is true that sigma j, uj, vj transpose is also in Rn times d, and this is also rank 1 for any value j. Okay, so I'm going to define there's going to be, and there are n by d matrices, so I can add them up. So AK is going to be the sum equals j equals 1 to k, which is going to be sigma j uj vj transpose. And this is again going to be an n by d. And it turns out that each of those terms are going to be effectively are going to be linear independent of each other. So this is going to be rank k, right? And so this gives me this best rank k approximation here. So this is how this is again defined by the subspace of all the right singular vectors, if you want to think of it that way. But this is how I recover an n by d matrix, which rank is only k. And this is what this so minimizes by the same arguments as before, a minus ak, the Frobenius norm, and a minus ak, the spectrum norm, under the condition that it's a rank k matrix, okay, for any input a. Okay, so that this is again the structure of this SVD here. There's another way of recovering it. Another way I like to think about it is I can take this S matrix here, and I'm just going to go down the top k of these here. And then I'm going to make these zeros. Okay, if you remember what happened here, I've got a V transpose, and I had U here. Okay, and if I remember that because these were already all zeros by definition, everything over here was already zeros. But now what I'm doing is I'm zeroing out this stuff, and that's causing this to be all zeros and this to be all zeros because I'm multiplying them by zeros when I'm recovering this. So what's left is going to be, again, an n by d matrix, but it's going to be a by k, right? And so in here, I'm going to get u1 up to uk, and this is going to be v1 up to vk, and here I'm going to get s1 or sigma 1 up to sigma k here. Okay, and so it's the same thing as I wrote just above here, but this is kind of a pictorial way of looking out. By zeroing out the singular values in this decomposition and multiplying it back together again, I again get a rank k matrix, and it's the same rank k matrix, and I get it by these zeros just zeroing out all these other components, which were less meaningful. Okay, great. Okay, so I want to spend the last I want to stop a little early, so I have about 15 minutes left to talk about the relation to eigenvalues and eigenvectors. Okay, so these were the 4 different ways of kind of interpreting what's going on with the SVD. And yeah, so hopefully this made sense. Maybe some of you have seen the SVD before. You've maybe seen eigenvalues and eigenvectors before. So let me explain the relationship with these, and hopefully this makes sense. But again, it's this operation you can call inside of whatever language, and it gives you this structure which tells you about the kind of the low rank representation which captures the most variation in the data. Okay, so let's talk about eigenvectors and eigenvalues. Okay, remember now this has to be kind of the input here has to be this square matrix M, which is going to be our n by n. So this has to be square. And then and what I have is, if I'm going to have m times v is going to be equal to lambda times v. Okay, so now this v is recovered. I multiply by a vector and I get a scale multiple of the vector. This v is then going to be an eigenvector, and this lambda is going to be an eigenvalue. That's lambda here. Okay, and so if M is positive semi-definite, then I'm going to have, or let me just say positive definite. Okay, then I'm going to have n eigenvalue, so vector pairs, and all eigenvalues are going to be real and so positive. Okay, and I'm going to say that each of these vi is going to be equal to 1. The norm is going to be equal to 1 is how we're typically, I mean, it doesn't have to here, but you can cancel this scale out. So we usually say the norm is 1, and we're going to say that vi dot vj, if I take the dot product, it's going to be 0. So these are going to be orthogonal to each other. So if I have a positive definite matrix, this is going to be true. If I have a positive semi-definite matrix, then this is going to be non-negative. So it's going to be non-negative. They could be equal to 0, and I'm going to say at most n. Right, so I might get, I guess I can technically get some where it's yeah, so it has to be at most m. There'll be some directions I might not have it might not be full rank. If m is not full rank, then there's some directions I multiply by anything in that subspace, and I'm going to get back 0. So those are going to be missing. Again, this is going to be connected to the singular value decomposition. Okay. So what's going to be interesting here, let's change this to, I think this will, because I used V here, D by D, okay? It's square, that's what's important, but we'll see why I use D here. Okay, so how do we give rise to these positive definite matrices? Well, we're going to do this in or positive semi-definite, we're going to do this in 2 ways. We're going to say MR is going to be given rise by multiplying a data matrix by itself, A transpose A. This will now be a matrix in R D cross D. And I can also do this the other way, equals A transpose, and this will be a matrix in R N cross N. Okay, so these guarantee, these is going to be if let's see, if A is full rank and D is less than N, then MR is going to be positive, so definite, and ML is going to be positive semi-definite. Okay, so I'm going to get these properties I want where all the eigenvalues are real and positive, or at least non-negative. Okay, the rank of ML, which is an n by n matrix, can be at most D. So I'm going to have a bunch of these. So I'm going to have these subspaces in there, which are going to be multiplied by a vector in that subspace, and the results can be 0. So I can't have eigen vectors in those subspaces. Okay. Okay. So when I start this way, right, which is within this class, we're always going to start with this sort of setup here. And let's start with MR written this way. Okay, I can say, let's again say that I have U S V transpose equals A, where this is from the SVD of A, right? So I've got US and V transpose here. And I want to look at what happens now where I take these right singular vectors. Okay, I'm going to take these right singular vectors here, and I'm going to multiply them by MR. MR multiplied by V. Okay. Okay. I can rewrite MR as A transpose A times V. And I can rewrite A by its singular value decomposition. That's going to be VSU transpose. When I transpose a product of things, I reverse the order and I transpose all the individual matrices. S is diagonal, so it's its own transpose if you ignore what those extra zeros are doing. And this one is going to be U S V transpose, and I have V here. Okay. Now something very cool happens after I've done this expansion. There's going to be two things I see. I'm doing U transpose times U and V transpose times V inside here. I can change the order I multiply these things. After I've done this expansion, I can change the order of multiplication. This is the identity matrix, and this is also the identity matrix. Okay, so that means what is going to come out of here is V, which is on the left here, times S squared. S times S. And it's a diagonal matrix, so I can think of kind of, when I multiply a diagonal matrix by itself, this is going to be V. What I get is sigma 1 squared, sigma 2 squared, up to sigma d squared, where these are going to be all zeros. Okay. So it's again going to be this diagonal matrix. When I square diagonal matrix, I just square all of its elements. But what's happened here is that I'm actually, if I think about these matrix Z, I multiplied. This is a bunch of vectors in this matrix V. Each one, when I multiply by MR, I'm going to get back with V times this. Pick a good color, times kind of some scalar value here, right? So what this means is that lambda 1, the first eigenvalue of MR is going to be sigma 1 squared. And in general, lambda J, this eigenvalue is the singular value squared. Okay, and the right singular vector, right? These right singular vectors, the Vj equals Vj. This one I think of as the eigenvector, and this is the right singular vector. Okay, so the right singular vectors of a matrix A are the same as the eigenvectors of A transpose A. Okay, so the eigenvectors and the right singular vectors are basically the same things after I've done this A transpose A, right? When I square it, I get I'm squaring it, I'm multiplying it by itself, I get a square matrix, and then I can define eigenvalue decomposition, and it's the same thing, right? It's giving me a basis in this d-dimensional space, and it's sorting them by the variance, but it's squared. So it's just the eigenvalues already have the squared component in them. When it's the singular values, I need to square those to get the squared component here. I feel like I may have forgotten some squares back here someplace, but okay, I assume it's going to be right in the textbook. For instance, like there should have been a square there. Yeah, so yeah, those are also squared. So kind of the squared singular values typically show up here. and the but the eigenvalues are typically don't need to be squared because the matrix has already been squared. Okay, so as I mentioned, when we're dealing with eigen square matrices in this class, they're usually arise by multiplying together two data matrices, right? That's happened inside of when we did the inverse inside of the linear regression formulation, we had that there. And here, when we're doing the eigen-decomposition, it's arising this way from data, and then they're corresponding with the singular value decomposition. Okay, let me just say two more things. Okay, ML, remember that this was equal to A transpose. This is in Rn times n. And I can again do ML now times this U matrix. And this is A transpose times U. And this is going to be US V transpose VS U transpose U. And if I factor out the, again, these same components, which are these identities, then I'm going to get back US squared again. Right, so again, so that means that when I do it this way, now the left singular vectors are going to be equals to the eigenvectors of ML, which is A transpose, right? So the same thing happens when I do everything in the transpose. These are just symmetric as before, and I still have that the singular values squared are the are going to be equal to the eigenvalues of ML, which this is A transpose. Okay, so I'm getting the same thing happening again, just when I multiply it the other way. In this case, because ML is going to be very rank deficient, it's not very high, you know, the rank is at most D. If D is smaller than N, then a lot of the eigenvalues are going to be 0 in this case. Okay, even if A is generated as a full rank sort of matrix. Okay, I want to mention one more thing. There's something called the Eigen-decomposition. Okay, and this is going to be for, let's say, M, which is going to be an R d by d. And I'm going to, basically, I can write M now as a product of V, L, V inverse, okay, where V is going to be, this is Rn d by d, and this is going to be orthogonal, and L is going to be a diagonal matrix again, also in R d by d. But it's going to be diagonal, and in fact, L is going to be equal to the diagonal of lambda 1, lambda 2, up to lambda n, where these are the eigen values. And here I can put zeros in them in case they aren't actually defined. And as long as V is going to be orthogonal matrix, I'm going to get just to fill out the basis. Because V is orthogonal, I know that the inverse is its transpose. So I VL V transpose. Okay. Okay. So it's really, I don't need to take an inverse to do this sort of decomposition. The other nice thing is that now I can define inverse. I basically have an algorithm. So I should say, instead of define, I'm going to say an algorithm for the inverse of, again, I have a square matrix. If it's a positive definite or positive semi-definite matrix, then I can do V, the inverse is going to be V L inverse V inverse as well. So the inverse of of a matrix which is a product. Let me write this out in 2 steps. This is V, L, V transpose inverse. And again, like a transpose, I'm going to swap the order of operations and take the inverse of everything. But the inverse is the transpose again. So this, basically this V transpose is coming down there. This one's coming down there. And we get V, L inverse, V transpose back again. So I just need to take the inverse of L. L is a diagonal matrix. So this is going to be equal to sigma 1 inverse, or lambda 1 inverse, lambda 2. So I can take the inverse of these by -1 up to the inverse. So I can take the inverse of a diagonal matrix by inverting each of the terms on the diagonal. And if these are zeros, then I just keep them at 0. Okay, so that's the last thing. Okay, so we've now basically have an algorithm for the inverse as long as we can calculate the singular value decomposition, which gives us the eigen-decomposition. Okay, so we almost have an algorithm for the inverse, which is the last missing piece of actually doing the linear regression, if you actually want to know how they fit together. And we'll do that in the next lecture. Okay, but before we sign off, I just want to say, I didn't want to say this during class. You're not working on it or sweating about it, but a lot of people seems to have had some challenges with this last homework. I checked right before the deadline. There was still like 30 people hadn't turned them in. A bunch of people sent me requests for extensions, and I granted a number of them for circumstances. I think it's that time in the semester. So I'm going to give everyone a 1-day extension on the homework. So I'm going to, after class, I'm going to move the deadline back. You always have a 24-hour late period or for 10% off and 48 hours for 20% off, but I'm just going to extend that for everyone. So if you felt rushed and you want to go and redo something, you didn't turn everything in, you can go and turn it in for the next 24 hours and you won't have a penalty on that. So I didn't want to say during class because then people are kind of working on stuff during class, so I'm going to do that, and I'm going to go update the deadline in Canvas right now that the lecture's over. All right, so that's the connection to eigen-decompositions. They're the nice case of eigen-decompositions. The singular value decomposition is the same thing. It'll be due tomorrow at 1:10, which Canvas will mark as 1:15. I'll just push it back exactly 24 hours. Yeah. And if you turned it in already, that's great. You don't have to worry about it, but yeah. Okay. Okay. Yeah, so